Have you ever wondered how a massive, decentralized system like Bitcoin can prove your single transaction is valid, without you having to download hundreds of gigabytes of data? Well, the answer is this really elegant and powerful data structure called a Merkle Tree. And believe me, it's like the hidden engine of trust for a huge part of our digital world.
All right, so here's our game plan. First, we're going to tackle the huge data puzzle that blockchains create. Then, we'll dive into digital fingerprints, that's hashing, which is the foundation of all this. We'll use those to build a Merkle tree from the ground up. After that, we'll see the real magic, how they verify data, where else you can find them in the wild, and then we'll uncover a pretty surprising flaw in the whole design.
So, let's start with the main challenge, right? In a decentralized world, trust is everything. But how on earth do you trust something when the entire record is just way too big for a normal person to download and check?
I mean, this is the million-dollar question. Picture this. You're on your phone. You've got a lightweight crypto wallet, and you just want to confirm a payment you received. How can your phone possibly check that against a ledger that's bigger than the phone's entire storage? It seems impossible.
Yeah, the scale of this problem is just immense. We're talking about a database that never stops growing. If you required everyone to download the whole thing, crypto would be totally unusable for most people. We absolutely need a way to verify one tiny piece of data without having to see the whole puzzle.
And the solution? It all starts with a core concept from cryptography called hashing. The best way to think about it is like creating a unique, totally tamper-proof fingerprint for any piece of digital information.
So a hash function, like the SHA-256 that Bitcoin uses, takes some data, say all the details of your transaction, and it spits out this short, fixed-size string of letters and numbers. That output, that's its unique digital fingerprint.
And here is the magic part. If you change the input data by even a single character, add a comma, change one number, the output hash becomes completely different, totally unrecognizable. This amazing property is what makes hashing the perfect tool for proving that data hasn't been messed with.
Okay, so now we have these incredibly powerful digital fingerprints. How do we use them to summarize an entire block full of thousands of transactions? Well, we organize them into this really clever structure, the Merkle Tree.
The process is actually pretty simple when you break it down. First, you take every single transaction in a block and you hash it. These become the leaves at the bottom of our tree. Then you take those hashes in pairs, stick them together, and hash that. You just keep doing that, hashing the pairs, moving up level by level until all the branches come together into one single hash at the very top. That final hash, the one at the very peak of the pyramid, is called the Merkle root. You can think of this single small value as a cryptographic summary of every single transaction in that block. If even one tiny detail in one transaction changes, the Merkle root will change completely. It's the ultimate fingerprint for the entire block. Okay, and this is where the real genius of the Merkle tree shines through. It's not just about summarizing data. It's about being able to verify a piece of that data with unbelievable efficiency using something called a Merkle proof.
So let's go back to our mobile wallet, right? It doesn't have the whole blockchain, but it does know the Merkle root for the block your transaction is supposedly in. So how can it use that one little piece of information to be 100% sure your transaction is really there?
The answer is the Merkle proof. See, to prove your transaction is in the block, you don't need all the other transactions. All you need is the hash of your transaction, plus the sibling hashes that sit next to it on the path all the way up to the root. It's just the specific breadcrumbs you need to rebuild that one branch of the tree. So your light wallet, your phone app, it does this quick little calculation. It starts with your transactions hash, combines it with the first hash it was given in the proof, and hashes them. Then it takes that result, combines it with the next hash in the proof, and so on all the way up. If the final hash it comes up with is an exact match for the official Merkle root of that block, boom. That's cryptographic proof. Your transaction is legit. And you know, this incredible solution isn't just some clever trick for Bitcoin. Merkle trees are a foundational piece of technology for making sure data is correct across all sorts of different systems. You'll find them in the distributed file system IPFS, making sure file chunks are correct. They're also super important for airdrops, letting a smart contract check if your address is on a huge list without costing a fortune in gas. Even massive systems like Amazon's DynamoDB and the version control system Git use them to keep data consistent. But, and this is a big but, as brilliant as the design is, a very subtle detail in how Bitcoin specifically uses Merkle trees creates a potential vulnerability, and it's one that a lot of people don't know about.
So the problem boils down to this. In Bitcoin's design, there's no real structural difference between a leaf node, which is the hash of a real transaction, and an internal node, which is just the hash of two other hashes combined. This means a 64-byte internal node can, if you're clever, be made to look exactly like a valid, but totally fake, 64-byte transaction. It's a case of mistaken identity.
Okay, look at this. On the left, that's the normal, honest way a proof works. You see the path from the actual transaction at the bottom all the way up to the root. But check out the diagram on the right. An attacker doesn't provide a proof for a real transaction. Instead, they provide a proof for one of the internal nodes, one of those hashes in the middle of the tree. They can trick a light client into thinking that this internal hash is the transaction. And because the math still works out and leads to the correct Merkle root, the fake transaction gets verified.
And this isn't just a what-if scenario. Researchers have shown how this exact flaw could be used to attack a blockchain like CoreChain, which relies on Bitcoin. By forging these proofs, an attacker could potentially mess with the entire consensus mechanism. That's the very heart of how the network agrees on what's true, and that could cause some very serious problems.
So what's the big takeaway here? Is that even with these foundational, battle-tested systems, the smallest details matter a lot. Understanding these fundamentals helps you realize why things like security audits are so important and how one tiny design choice can have massive real-world consequences.
It really leaves us with a powerful question, doesn't it? As we keep building the future on top of these cryptographic tools, what other basic assumptions have we just taken for granted that might be worth re-examining? What other simple, elegant ideas might be hiding a complex and dangerous flaw?